Welcome to the Applied Machine Learning for the Cybersecurity, a hands-on YouTube video tutorial series specially designed for the data and machine learning engineer to help them to solve the critical challenges in the cybersecurity space by applying the modern machine learning and data engineering techniques. This is the fourth and final video in the section 1 and the fifth video in this series. If you haven't seen the previous video, then I would recommend you to watch it first for having the better understanding about the series before continuing any further on this path. You can watch it either by clicking on the link given in the below description or by starting with the first video in the playlist. A quick recap on what we had covered so far. First, we had a brief intro to the cybersecurity and we learned about the different types of the cyber threats. Next, we talked about the importance of the machine learning in the cybersecurity world. After that, we talked about the course structure and the layout of the series. Then we had set up our development environment using Docker, Conda, kubectl and Intellij. After that, we had created the Docker images and discussed about the best practices around the Docker and apply them to optimize the size of the Docker image. Next, we learn about the vectorization, dimensionality reduction and clustering techniques, and we had labeled the raw data using unsupervised learning technique. After that, we had discussed about the unsupervised versus supervised learning with an example of clustering versus classification. Next, we looked into the different vectorization and normalization techniques. And finally, we had done few exercises on the malware classification where we had compared different classifiers with the help of accuracy and other performance matrices. In this tutorial, we will continue with where we have left off in the last video on malware classification, and we will discuss about the importance of the AutoML framework and will also see the demo for the same. What we had used in the last exercise is just the default classification models with default parameters and calculate the accuracy based on it. But in real world, we have to calculate the accuracy on these models with the different parameters to gain the maximum performance out of it. This is the iterative process and it takes a lot of trial and error to process. And we have to try each classifier with various permutations and combinations of the different parameter, and this process is called hyperparameter tuning. Hyperparameter tuning is quite tedious and lot of effort goes into automating it, and that's where the AutoML framework comes into the picture to rescue us from this tedious process. Although AutoML framework does much more than just hyperparameter tuning and model comparison, but definitely this is the most important aspects of the AutoML framework. Also, whatever the model we have come up with is not always permanent in nature and it is subjected to change based on the amount of data we have used in training and few other factors. And as an ML engineer, we have to make sure that we have always picked up the best model and deploy it in the production for real-time prediction. This is also quite challenging task to manage, and thankfully AutoML framework can help us to solve this problem as well by exporting the best model to the known location like S3 bucket or some REST endpoint from where the production pipeline can pick it up. There are many AutoML frameworks are available in the market today, and they all are trying their best to get the major market share by providing various features, and here I am mentioning top 3 among them, and those are: first, AutoScaLearn. AutoScaLearn is an AutoML framework based on the open meta learning and ensemble construction to find similar data pieces. The package includes 15 algorithms for the classification and 14 for the feature preprocessing to define the right algorithm and optimize its parameter with the accuracy of more than 0.98. AutoScaLearn works well for the small and medium dataset. However, it doesn't provide enough scalability for the large dataset, hence it is not suitable for the large scale production pipeline. Second is Teapot. This framework uses the generic programming to search for the model for specific task implementation. It can analyze thousands of pipelines and provide the one with the best option of the Python code. In comparison to the AutoScaLearn, Teapot offers its own regression and classification algorithm, but since it is built on the generic programming, the model can give you the different results for the same task every time you run it, and that's the problem. And the third and the last one is the H2O AutoML. H2O uses the statistical algorithm with the gradient boost machine and complex learning system, and it also supports deep learning frameworks as well. It is definitely a leader among available AutoML frameworks in the today's market and consistently releasing the new features over the time. In this series, we would be using the H2O AutoML for proof of concept and also for the real-time production scenario using the Spark. Finally, let's jump onto the lab with H2O AutoML in action, and first we will build the Docker image for this exercise, which will be based on the previous Docker image we have created. We can open the redeem file associated with the chapter and execute the given command to build our new Docker image. Now that our Docker image has been built, let's run it and launch the Jupyter Notebook. Let's upload the IPython notebook and associate dataset to the Jupyter server. Now let's run the notebook section one by one while discussing the same. The first section is to import the H2O module and initialize the same. Once H2O is initialized, you can see that it's running in its own context on port 54321. In the next cell, let's create the H2O data frame by importing the dataset. H2O data frame is equivalent to the pandas data frame, and we can perform all the pandas operation on it. Next, split the train and test data into the 80-20 ratio and create the H2O AutoML object. Some important parameter to consider is the max model, which tells H2O that how many top ML models we wanted in the output. In our case, we are seeing that we are only interested in top 5 models. The next important parameter is exclude algos, which tells the H2O that which ML algorithm we would like to skip for the time being. In this case, I am excluding the deep learning and stack sensible, as we are going to cover them in a great detail in the next future video. Once initialized, let's run the training and find the top performing ML model by looking at the leaderboard, which shows the model sorted based on the lowest RMSE, which is root mean square error, another performance measuring criteria like accuracy we had seen in the last video. If you look into the above result, then you would find that XGBoost again outperform other algorithm, which is H2O had done the same thing as we had done manually, but had abstracted lot of complexities from us. In this demo, we will cover only this much of the H2O, and we'll have more exercise on the H2O AutoML framework in the next section, where we would be using H2O sprinkling water module along with the Apache Spark. At this point, we have some better understanding on machine learning, where we can differentiate between the supervised and unsupervised learning, know how to compare and pick up the best model, also know that how to tune the algorithm using the hyperparameter. It is the time to venture into the real-time production use cases. So far, we have learned and evaluated machine learning concept via scikit-learn, which is good for dealing with the few megabytes size of the data and to do the initial proof of concept, but it's not the ideal framework when it comes to the real-time production scenario, where we have to deal with the terabytes or even petabyte scale of the data. There we have only 3 choices. The option 1 is using the distributed technologies like Apache Spark, which runs on the clusters of machines running multiple CPU cores. Option 2 is using the GPU supported technology like Rapids, a drop and replacement of the scikit-learn based on the CUDA framework for the GPU. And the third one is the deep learning frameworks like TensorFlow or PyTorch, which supports the GPU accelerated training. Deep learning frameworks can run on the CPU as well, but its out-of-box support for the GPU had got more tractions. With this, I am concluding the current chapter and as well as the current section 1. And I hope you have understood that how to use the H2O AutoML to find the best model for doing the ML prediction. See you in the next section, where we would start implementing the real-time production scenario. And at last, please leave your comment and let me know your feedback about the current video, and please subscribe the channel if you haven't. That way you can always get the first handle on any upcoming video as soon as it's been released. Thank you and have a nice day.